Okay, let's start with another question. And here it says, what is the maximum error possible in using this approximation? Now I'm going to use a different method than the previous one. Now remember, for the previous question we basically used this relationship, but here in this question I'm going to use a different technique, and in the next video I will explain how to use that previous result, and also I will explain why we cannot use the method that I am going to do now. Let's name it as method 1, and I will explain why we cannot use this method for the previous question that we discussed. Okay, so this method is basically on the alternating series estimation theorem. So if you don't remember that one, please go back and refer to those lecture materials. Right, so let's go over the question one more time. Here it says, what is the maximum error possible in using the approximation? So basically we need to find the error caused by this approximation. Now sin x is the original function, so we are going to approximate it with this finite number of terms. So now also there's another thing that you should notice when you have this polynomial. It is the 5th degree Taylor polynomial, and if you don't see why, please go back and refer the lecture material that I introduced the nth degree Taylor polynomials. Okay, right. So now here it asks, basically for the first method we don't need this data anyway. Now what it asks is, if we use this approximation for this particular region of x. Now let's see, if we plot the graph, this will be the sin x curve, right? And now this is, like, we already know that it has a oscillating shape, right? And if we plot that polynomial, it will look like this in the green color. So you can clearly see that there is a certain region that the values from the polynomial and the values from the sin x function will look alike. Right, now I am not saying that they are exactly equal, but they are almost the same. But if you zoom in, you can see that there is a certain difference. See, now if you zoom in like very close, you can see that there is a certain difference, but it will be a very good approximation. Basically that's why we use the word approximation. Okay, so we are not finding exact values, but instead we are taking some very close figures. Okay, that's the kind of the basic meaning of the word approximation, right? Okay, so the question asks, what the meaning of the question is, now if we use this green colored function, what will be the maximum error that it can cause? Now also you should see that the error will be significantly large if we choose a point somewhere in between -5 and -10, or else somewhere in between +5 and +10, right? Because the sin x values will be within 1 and -1, but the green colored graph is somewhere else. So from this picture, what you should understand is the errors will totally depend on the region of x that we choose. But here in this question, it asks for this region, right? Now, if we take that diagram into our page, you will have this one now. So the region that they have given is in a very, in this nice interval, right? So it makes sense to use this approximation in order to calculate the function values within this region. But it's not good to approximate values somewhere here through this this fifth degree Taylor polynomial, right? Okay. Well, I think I have made some mistake, because now this is the fifth degree Taylor polynomial, but I chose the seventh degree polynomial. What I should have chosen is this one, right? Okay, so sorry for that. Let me take that image to our paint window. Alright, there you have it. Okay, anyway, this small interval is a nice region, right? Within this sort of range, you have a very good behavior for the fifth degree Taylor polynomial, right? Okay, so now how do we find the maximum error that it can cause? For that, now remember in the previous question we used that inequality, which is this one. But here what we are going to do is, we notice some other property in this given equation, and for that we will need the Taylor series or the Maclaurin series of sin x. Remember, we have this sigma notation, the concatenated form for the Maclaurin series of sin x. And if you don't remember this one, you have to have this format in your mind, okay? Right. Please go over these theories if you don't remember them, okay? Because they are very important and some fundamental relationships that you should have in mind, right? So by looking at this one, we can make some more conclusions. That is, if we choose an x value from here, let's say for instance, if we choose, now our region is this one, okay, negative 0.3. now let's choose x equals negative 0.2, which is within this interval. Then our Taylor series will be something like this: negative 2 minus negative 0.2 cube plus negative 0.2 to the power 5 minus negative 7. Likewise, it goes on, right? Now the important thing here is that you have a odd power, right? Therefore, when you have a negative number inside as the base, you can take out the negative coefficient, right? So ultimately what you will have is something like this, right? 3 over 3 factorial negative 0.2 over 5 factorial plus 0.2 over 7 factorial. Likewise, you will get an alternating series, right? Therefore, we can use the alternating series approximation theorem. So now you can see that the approximated terms given here in this question are from x to the power 1 up to x to the power 5, right? That's the thing that we have to use. and basically that is this graph. Okay, so from the alternative series approximation theorem, it says if we can have an inequality for this one, it will tell an error bound for these terms, okay, for the addition of these terms. So basically what we have to compare is the maximum value that this can achieve, because then from the alternate series approximation theorem, it gives a error margin for the addition of the previous terms. That's what alternating series approximation theorem says. And if you don't remember that theorem, please go back and study it and then come back to this problem. Okay, right. So now when you take this term, you can see that x to the power 7 over 7 factorial will be, now if we take the modulus, that will be equal to the modulus of this number, right? And also we know that we are choosing x within this region, right? So for these particular x values, the maximum that this can achieve is when you substitute the 0.3 in here, because x is there only in the numerator, and when the numerator increases, the total value will increase. So this is the maximum number that it can take, right? And that is equal to 4.3 times 10 to the power minus 8. Okay, therefore from the alternate series approximation theorem, it says that the addition of first 3 terms will give an error less than this amount, or in other words, when you compute T5, right, when you compute the 5th degree Taylor polynomial, the error caused by that will be at most this amount. When T5 is considered, the error will be at most this amount. Okay, so this means you have 0.00043 and you will get 7 zeros in here, right? So it will be approximate, it will be equal to, or in other words, it is accurate up to the 7th decimal point. So it's a very good accuracy, right? Actually, whether it is good or bad is decided depending on the experiment that we are conducting. Okay, if it is a micro scale, this might not be that suitable, but if it is a macro scale, that means something like a planetary distance, this will be a very good accuracy, right? Okay, and then now for the answer of this question, what is the maximum error caused will be equal to this amount, right? So the maximum error that it can cause is this amount, or in other words, if you look at the graph and when you choose points in between negative 0.3 and 0.3, the maximum difference that the two graphs can take will be this amount. Okay, so it's very, very close to each other. So here also, if you focus on a point like this and if you keep zooming on, you can see that you will have to zoom quite a lot to see a difference, right? See, still you don't see a difference. Okay, now I lost the track. See, still you don't see any difference. Not yet. you will have to, now you can see a difference, right? See, you will have to zoom quite a lot to see a difference between the two graphs, right? So it's a pretty good accuracy, right? And then it asks to use this approximation and find the value of this one correct up to 6 decimal places, right? Now we already know that we can approximate the sign values through this one. So what we do is, in order to calculate sine pi over 15, we substitute it in our polynomial approximation, right? So when you use the t5 and calculate the value of t5 at pi divided by 15, it will be equal to this amount. And as we know that it is even correct up to the 7th decimal place, but here in the question it asks to find the approximation correct to 6 decimal places. So what we can do is to cut this number up to the from the 6th decimal place, what we can do is we can use round off techniques to end this number from 6 decimal places. So definitely this will be accurate up to the 6th decimal place. And the next question asks, for what values of x is this approximation? That means this one is accurate to within 0.00005, right? Now here you only have 4 decimal places, right? Now in our original question you had I think 7 decimal places, right? So in other words, now here in the part B of this question, they have relaxed the accuracy. Now this is not accurate as it is in the first case, right? So here you only have 4 decimal places, but in the original, I mean in part A, you had an accuracy of 6 decimal places. And to get that 6 decimal place accuracy, we were within the range of, I mean the interval of the x values that we chose was between 0.3 and negative 0.3 and 0.3. So within this interval you have an accuracy of 6 decimal places. But how about for 5 decimal places? That means we can get the natural idea that we can expand this range of x values that we consider, right? Because if we keep on expanding these x values, you will have a higher error margin. Say for example, if we take somewhere here and somewhere here, the maximum error that it can cause is, now see, for this particular x value, the correct number is this one, but if you take the approximation, you will get somewhere here. So the error will be this amount. Okay, so expanding this interval means you will be increasing the error as well, right? So now here in the question it asks to do the approximation, I mean to find the suitable region so that the same approximation, that means we are not changing the graph. Okay, so we have to use the same approximation, but we need an error only within this amount. So basically that means we are going to increase this range, because when you increase the range, we can clearly see that the error will also increase, right? So to do that, we simply have to use this approximation alternate series estimation theorem one more time. So from that theorem we already know that the error of this one, which is the given term, the error of t5 will be the upper bound for this number. So what we have to do is we have to find the suitable x values so that this upper bound is less than 0.0005. So then alternate series approximation theorem will says that the error of T5 will be less than this amount, because this is what the theorem says. Okay, so basically our task should be to find the suitable x values so that this inequality is satisfied. That means if we just multiply this 5040 throughout this inequality, you will get x to the power. So now to do these calculations you will need a calculator. Okay, you are not expected to do everything manually, and the modulus of x will be equal to 0.252 to the power 1/7, and that is equal to 0.821, right? So basically what we have is the modulus of x is less than or equal to 0.821, right? That means if we draw the real number line, we have these two should be of equal length. Sorry for that, these two should be equal length. Here you have negative 0.821 and here you have positive 0.821, and if we choose an x value from this region, this calculation will tell you that this is less than this amount. That means the error will be less than that amount. In other words, if we choose numbers within these two intervals, these two values, that is, see, initially we had negative 0.3, but now we have expanded our interval of concern, right? Actually the places that I have marked is not that correct. Okay, so if we draw this more accurately, 0.03 will be somewhere here and 0.8 will be somewhere here, right? So it will not go beyond these largely deviated regions. Okay, right, so basically that's it for this problem, and in the next video I will explain how you can use the previous method that we did in the previous video for this question, and also we will see why we cannot use the alternating series approximation theorem for this previous question.